Okay, so just going to test quickly the sound quality here. Okay, so this video is 3.1a and it's talking about extrema on an interval. So that's what we're trying to do. We're trying to find extrema, which means extreme values, maxes, mins, relative maxes, relative mins, local maxes, local mins, absolute maxes, absolute mins, and just maxes and mins in general. And all of that vocab can be confusing, but what I want to show you is how to find if there was a closed interval, so like just a certain interval of x values, and I wanted to find the highest or the lowest value, right? Well, let's just draw a couple of functions here. Let's just try to get an idea of what's going on here. So if I had a function like this, and that's the interval, so here's the start right here, and here's the ending of the interval. And if I had one like this, right, you might say this is the start and this is the ending. And where could the maxes and the mins actually occur? Where could that happen? Well, you'll notice actually on this one right here, there's a maximum here because there's a hill there. You'll notice there's a local minimum here. Locally, it's like a hill, but it's not like global, like Mount Everest, right? Globally, this is the absolute minimum, for that interval. You'll notice here that the max in this case is the end, and here the min, I think, is this point right here, this bottom, this valley. So what I want you to think about, and my apologies if this goes off the screen. I'm recording on a square screen, but I'm trying to record widescreen, so that might happen. You'll notice these hills and valleys are happening here, and it's kind of interesting. So let's kind of just do some work with this and see what's going on. So I'm going to get rid of all this stuff, and we will start finding the critical numbers of this blue example. So how do we do it? Well, I'm telling you how to do it each time. So take the derivative and then set that equal to 0, and then solve for x. Or find values where the derivative doesn't exist, right? So that could be another place where you'd find it. So let's take f prime of x, which is going to equal 3x squared minus 12. That's really it. And we want to set that equal to 0. Well, 3x squared minus 12 is just a parabola. It's not going to have any places where it does not exist. That's not going to be a situation here because it's not like an ln, it's not a trig function, it's not a rational function with a denominator. This is actually a nice straightforward function, and all we need to do is find the values of x here. Those are where the derivative is 0, because we found the derivative. That's where the slope is 0. So what I'm going to do here is I'm just going to take out a 3, I'm getting to x squared minus 4 is equal to 0. And what x's are going to work here? Well, if we go this way, because I'm running out of space already, I'd have x plus 2 and x minus 2 would equal 0, right? So we can find out pretty quickly that our critical numbers are x is equal to 2 and x is equal to negative 2. That's what's going on here. So these are our critical numbers. That's step 1. Now we want to keep moving. So why are those numbers important? Well, that's either going to be that x equals 2 is telling us that the derivative is at a top of a hill, right? Here. Or maybe the function is at a valley. Because you'll notice that at the top of the hill, the slope is 0. At the bottom of the hill, the slope is 0. So let's see what we can do with these numbers. So basically, we want to evaluate the original function at each number, and the original function was x cubed minus 12x. So if I take the original function, which was x cubed minus 12x, and I take my critical numbers, which were x equals 2 and x equals negative 2, we know that these are potential maxes or mins. We're going to call them candidates. That's why it's called the candidates test. It's also called the extreme value theorem. So we're just going to take those numbers and see if we get something really high or really low, because that's a potential hill or a valley. Actually, it pretty much is going to be a hill or a valley, I would say. It's pretty safe to say that. So I'm just going to find f of 2, the function when we put in 2, how high or how low is it? So that's 8 minus 24. So that's negative 16. And I'm going to find f of negative 2, which is going to be negative 8 plus 24, I think. So it's going to be 16. So we've now found that this is the y value when we put in 2 and when we put in -2. So those are two y values that are of interest. We need to see if those are the highest y values we can possibly get or the lowest or whatever. And if we look back at that diagram, we saw that we can get a max or a min on an end of an interval as well. So we know that this interval is ending. Where is this interval ending? Well, let's look at it. Well, they said from 0 to 4. So actually, right now, I'm looking at this interval is from 0 to 4. This is the world we're living in. Does this x equals -2 really matter to us? No. So I'm going to go down here and I'm going to say that this is really kind of irrelevant, right? We didn't need that because our interval, that's outside of the interval. So it can't be a max or a min on the interval there because we're only going from 0 to 4. Okay. Now we want to look at the endpoints. So we want to know what happens with the function at 0. Does it start out really low or really high? And we want to know what happens with the function at 4. So I think it's x cubed minus 12x. So I'm remembering that. 0 minus 0. So that's 0. X cubed 64 minus 12x. I guess that's right, hopefully. And that is, let's see, 16, is it? So here's what I've got, and we carry over from earlier. We said that f of 2 was equal to something as well. We had that. So let's see what we said f of 2 is equal to. -16. So f of 2 is equal to -16, so let's keep that with us. So it's pretty simple. All we have to do is look at these values right here. These are the heights. This is a height of 0, this is a height of 16, this is a height of -16. Which one of these is the smallest? That's our minimum. So it's pretty straightforward. Do I have a highlighter here? I think I should. Okay, well, I'm not going to waste time on that. So what I'm saying is the least of these is the minimum, right? So the least one is the minimum. Scribbles over it, darn. So the least is the minimum, and this is the lowest value. So we have a min of, I guess what I'm going to say here is I'm going to say min of -16. That's as low as it goes. I'll say when x is equal to 2. That's our minimum. I'll use red for that. Now we'll use green for our maximum. Well, this is our highest y value. So I'm going to say I have a max of 16 when x is equal to 4. And there's our minimum, and there's our maximum, and we've done it. We found the minimum and the maximum on the interval. We know that this is an endpoint, so it starts out, apparently this function starts out really high at 16. And then it drops down to 0, and then it actually drops to -16 at 2. So it must start out high, it drops down to 0, it drops down to -16, then it starts to pick back up, and it goes back up. I think after 2 it goes back up to like 16 eventually, right? So we go up to here. So my mistake, we start out at 0 right here. Okay. Then we go down to -16, and then we finally wind up at +16 over here. So there's our max, and there's our min. Okay, this is when x is equal to 4, and this is when x is equal to 2. So don't overcomplicate this. It's pretty straightforward. The values where the derivative is 0 or undefined are going to be helpful for you in finding the max and the min. So as we go on, I want to talk about a couple of things. This is really not as bad as you think. All this is saying is that the minimum happens, right, on the minimum of the function on an interval if the value of the function is greater than, that minimum for every x in the interval. So in other words, if you have like a hanging rope and this is the minimum, we notice that every y value up here is higher and every y value over here is higher as well. So that's what makes it a minimum. Maximum on an interval if all of the function values are lower than that except for that value, if that value is the biggest, greater than everything else. So that's pretty straightforward. I'm going to talk about a couple other things because this is really just really wordy. So we know about relative and local maximum, relative and local minimum, hopefully from pre-calc. And the next thing I want to talk about, this is really just vocab, so just kind of get an idea of it. I don't know how important it is. I want to talk about a couple of things though. When you have an open interval, right, like, you know, it's closed on one side but it's open on the other, right, and we have values here. Let's just say A and B, we don't know what they are, like 2 and 7 or whatever. You can't really find a max or a min here. This is not a min. Because what happens is when you kind of like go in here and you kind of like look closely at this area where the star is, you'll realize that you can't really put your finger on what that value is. Even if I put a dotted line in here, right, and I said, ugh, terrible. Even if I did that, this is hard really on this tablet that I'm using. If I said that this, right here, this value was, for example, I don't know, let's say it's 2, right? I can't say that the minimum is 2 because it's open at 2, where that dot is. I can't say the minimum's 1.9 because the minimum could really be 1.99. Or maybe the minimum would be, see, 1.9, 1.99, 1.999, 1.99999, 1.99999. We can never really pinpoint, stick, or find that minimum, so this is not a minimum. Even though it's lower, it cannot be classified as a minimum because you can't find that value. You'll notice that this is the maximum, and you might say, hey, the derivative doesn't exist there. So it's possible that where the derivative doesn't exist, that's where you have a max. Now you'll say, hey, I have a derivative that's 0 here, but it's not the min or the max. It's just a relative min. This is a relative max. And this is, it's not the minimum, I wouldn't say. I would not say this is the minimum, but I also wouldn't say it's like a local min or local max. This is a little bit of a tricky point to think about when we're doing this. We have to consider, what is that? Is that a minimum? Is it a local minimum? Is it neither? I don't know. I guess we'd have to look into that a little bit before we could really say. So I don't know. Let's leave it as an open question. I think that's okay. So the last thing I want to talk about is just like extrema is like a really confusing thing with all the vocab. There's tons of different types of extrema, right? So I want to just make a little flow chart here so you can see. So there's like all sorts of types of extrema. So like we have relative, right? We have relative. And relative extrema is pretty straightforward. Like on relative extrema, there's a local, or you call it a relative, max. Or you could have a local min, right? Sometimes people just call it the max or the min. You could also have an absolute. And when you have an absolute, people just call it straight up the max. So like a max is just a shorthand way of saying it's the absolute max. Or it could be the min, right? Or it could be of course you could call it the absolute max, or you call it the absolute min, right? Absolute min. And all of this is extrema, right? So we have absolute extrema, and relative extrema. We have relative and local max, relative and local mins. That's like Mount Wachusett. Okay, that's the local max around here. That's the highest point in like central Mass. It's like one of the only areas that's like a little bit higher. And maybe I'm wrong on this. Let's just pretend I'm right. So we got that local max, but we know that that's not the global max. That's not the absolute max. If we're talking about the absolute max in the US, we'd say Mount Washington. But if we're talking about the absolute max in the world, we'd say Mount Everest. If we're talking about the absolute max in North America, we might say, I don't know what it is, but it might be Mount Rainier or something like that. I don't think it is, but you get the general idea. So absolute max can happen in whatever country you're looking in, or whatever. If you want to look in the state of Massachusetts, then it could still be the absolute max in Mass. So you got to remember there's relative maxes all around. My parents' house is on a hill, and that's a relative max for around there. but there's also absolute max. So there's a little bit of a difference between those. I don't think we need to talk too much about this really. So this is just that same picture. We can kind of wrap it up there. So just follow those procedures, rewind, check it out, and hopefully that was helpful. I don't think there's anything really else to talk about. I mean, these are kind of interesting examples. Yeah, fine, fine. So you're good. So what I want you to remember is the vocab also critical number. That's when the derivative is 0. So call those or undefined or undefined. Critical number when the derivative is 0 or undefined. All right, let's wrap it up there. I will talk to you soon. Peace.